Welcome back to statistics. So we've seen some of the basic ideas of significance tests, including the ideas of formulating the hypotheses of the tests and also the relationship between two-sided significance tests and confidence intervals. So now I want to dive a little bit deeper and look into some of the new ideas involved in significance tests. And this includes the important idea of the so called p value of a test. We know that we reject the null hypothesis when the data are extreme, assuming the null hypothesis is true. And the p value is a measure of how extreme the data is. And so that'll be one of the ideas we talk about here. So let's take a look. Significance tests, test statistics, p-values, and critical values. So these are all tools that are used in testing the hypotheses. And this simply means when we talk about testing the hypotheses, we're talking about seeing how the hypotheses line up with the data. Are the data consistent with one or the other of the hypotheses? In testing the hypotheses for a two-tailed test, we know that the confidence interval approach can be used. So there you compute, say if you're at a 5% significance level, you would compute a 95% confidence interval, and you would see whether the null value, the value for mu that's in the null hypothesis, is in that confidence interval or not. If it's not in the confidence interval, that says the null value is not plausible given our sample data, and therefore you would reject the null hypothesis in favor of the two-sided alternative. If, on the other hand, the null value were in the confidence interval, then that says the null value is entirely plausible and there's no reason to doubt it, so you would fail to reject. For one-tailed tests, a new idea is required to actually carry out the test, and that's the idea of the p-value. P-values also work for two-tailed tests, and actually we'll be illustrating p-values in a two-tailed test in this video. In a subsequent video, we'll come back and look at one-tailed test and see how the p-value works there. So p-values. The essential idea of a p-value is to measure how extreme the data is relative to the hypotheses of the test. So let's consider an example that we've seen before. This is the chocolate coated sugar bombs example we have discussed. The null hypothesis was that the average amount of cereal in a box is 32.4 ounces. And the alternative is that it's not, and it the mean could be either less than 32.4 or bigger than 32.4 if some problem happens with the production machinery. And so we want to see how these hypotheses line up in light of the sample data, which was that an average weight of 32.5 ounces per box was obtained in an SRS of 25 boxes taken from the production line. And here we're assuming a known value of sigma for the population of 0.2 ounces. I want to emphasize that this is all tied to the fact that we have a two-tailed alternative here. And again, we'll discuss what modifications need to be made to the procedures we're about to see if the alternative is a one-sided alternative. So, as we've seen before, the first idea is to assume the null hypothesis is true and see where the observed data, our observed x bar value, falls in the sampling distribution of x bar. So here you see the sampling distribution. It's normal with a mean of 32.4 and a standard deviation of 0.04. And remember, that comes from the fact that this is the sampling distribution of x bar. The standard deviation of x bar is sigma over root n, 0.2 over the square root of 25, or 0.04. And you can see where our data lies. It looks like it's extreme, and it's certainly outside the middle 95%. And so our data wouldn't be extreme, assuming the null hypothesis is true. You could say this in several different ways. The data is not consistent with the null hypothesis that mu is 32.4 at the 5% significance level. Or you could say that assuming the null hypothesis is true, the data is extreme at the 5% significance level. These are all really different ways of saying the same thing. If the null hypothesis were true, the observed data would be highly unlikely. If we want to think about the idea of the data being extreme, it's natural to ask, how extreme is the data? Can we measure that? And a good way to do this, it turns out, is to look at the z-score for the data. In other words, the z-score for x bar. Now, let's think about that for just a minute. We know that the z-score is the data value minus the mean over the standard deviation. You just have to remember to use the standard deviation that's appropriate for whatever variable you're looking at. Here we're thinking about x bar. So when we're talking about the z-score for x bar, we need to use the standard deviation of x bar. So that's what you see in the formula. The z-score for x bar is x bar minus mu divided by the standard deviation of x bar. But we know the standard deviation of x bar is sigma over root n. And so you often see that right-hand piece of the formula, x bar minus mu over sigma divided by root n, in text as the formula for the z-score for x bar. But it's really just a z-score. You just have to remember to use the standard deviation for x bar. In our case, what would that turn out to be? Well, our x bar is 32.5. The value of mu from the null hypothesis is 32.4, and the standard deviation of x bar is 0.04. So you get 2.5 as the z-score for our data. Now let me go ahead and change the graph from normal 32.4, 0.04 to a graph that can show that z-score. We're talking about a z-score, so of course that would be the standard normal distribution. And here you see our data expressed in terms of the standard normal distribution. Again, our z-score of 2.5 corresponding to our observed x bar of 32.5. Still exactly the same position in the tails and so on. We've essentially just changed our units of measurements here. The z-score for x bar is called the test statistic for our significance test. And that's an important idea going forward. The test statistic is, in essence, the number of standard deviations that x bar lies above the mean. And we again want to come back to this basic question of how extreme is our x bar. That's equivalent to how extreme is this particular z-score. So let me just remind you one more time of that formula for the z-score for x bar. That's the formula for the test statistic. To discuss how extreme it is, I want to just kind of compare it to a couple of other z values that we could have gotten but didn't. So for instance, suppose we look at our z-score of 2.5 and compared it to a z-score of 2. Which is more extreme? Well, our z-score of 2.5 would be more extreme than a z-score of 2 because it's further out in those tails, and the tails are what defines what's extreme here. So 2.5 would be a more extreme test statistic than 2. In the same way, 2.5 is a less extreme test statistic than a z-score of 3, because 3 is now further out in the tails than our z-score of 2.5. Consider a z-score of negative 2.5. we would consider this precisely as extreme as our z-score of 2.5. Why? Well, it's because it's exactly as far out in the tails, right? A z-score of negative 2.5 is exactly as far out in that left tail as a z-score of 2.5 is out in the right tail. So we would consider negative 2.5 to be exactly as extreme as our z-score of 2.5. And in the same way, we would consider a z-score of negative 2 to be less extreme than ours because it's less far out in the tail, while a z-score of negative 3 would be more extreme than a z-score of 2.5 because it's further out in that tail. So what is a p-value then? A p-value is the probability of all data that's at least as extreme as the observed data, where again, extreme means as far out in the tails. So the data that's at least as extreme as 2.5, our z-score, would be any data that has a z-score of 2.5 or greater or negative 2.5 or less. And you could compute the probability of that data just using standard software calculation tools. Be the probability of a z-score that's either less than or equal to negative 2.5 or greater than or equal to 2.5. And that turns out to be 0.01242 or about 1.242%. So the p-value is defined this way. It's the probability of all data at least as extreme as the observed data. One thing I'd like to point out here, and let me go back a slide to do this, is that as the data becomes more extreme, right, further out in the tails, the p-value gets smaller. So small p-values correspond to more extreme data. The smaller the p-value, the more extreme. These ideas have a relationship to statistical significance as well. Recall that at the, say, 5% significance level, we would reject the null hypothesis in favor of the two-sided alternative precisely when the sample mean lies outside the middle 95% of the sampling distribution. An equivalent way of saying this is that we would reject the null when the test statistic lies outside the middle 95% of the standard normal distribution. So I've got that middle 95 there labeled. The tails represent the extreme values, and the area of those tails together is precisely 5%, right? Because it's what's left over from the middle 95%. So that the area of those tails that define what counts as extreme at the 5% significance level is precisely 5%. It's precisely our alpha value. You'd have 2.5% in the left tail and 2.5% in the right tail. If you have a observed X bar whose z-score lies in those tails, then you're going to reject the null hypothesis, right? You're outside the middle 95%. Now, think about the p-value that would be associated with an observation like that. Remember, the p-value is the probability of all, in this case, z-scores that are at least as extreme as ours, at least as far out in the tails as our z-score. I've shaded those tails in here red, and you can see that would be our p-value, the area of the red shaded region. Clearly, that area is got to be less than our significance value of 5%, right? Because we're inside that region. And so this leads us to another criterion for determining whether or not to reject the null hypothesis. The so-called p-value criterion says that we reject the null hypothesis at a significance level alpha if and only if the p-value is less than alpha. And I think you can see why, right? The only way the p-value could be less than alpha is if the data were out there in those tails. If the tails have area 5% and our data is in the tails, then the p-value is going to be less than 5%. For our particular example here with the chocolate coated sugar bombs, our p-value was 0.01242, and that is indeed less than our alpha value, which was 0.05. So we would reject the null hypothesis that the mean is 32.4 in favor of the alternative that the mean is different than 32.4 at the alpha equal 5% level. So the p-value criterion provides you with a second and completely equivalent way of determining whether to reject the null hypothesis. Reject if and only if the p-value is less than your significance level alpha. Let's relate this to another idea we saw in the context of confidence intervals, and that's the idea of a critical value. For significance tests, the critical value essentially marks the boundary of statistical significance. Let me explain that by considering a two-tailed test again at the 5% significance level. So here I'm showing the z-scores, and the shaded region corresponds to values that would cause us to reject the null hypothesis, right? I am assuming that sigma is known here. If sigma weren't known, we would have to use the t-distributions, which we'll discuss in a few minutes here. That shaded region is called the rejection region for the test for the obvious reason that if you're in there, you're going to reject the null hypothesis. What test statistic z defines the boundaries of this rejection region? Well, you could easily calculate that, right? That value z is just the value that defines the middle 95% of the standard normal distribution. That was the value we calculated as the critical value for a 95% confidence interval. Now, when we're talking about a 5% significance test, we still call it a critical value. It still has exactly the same value, but the interpretation now is that that number defines the boundaries of the rejection region, right? The rejection region would be anything bigger than our z-star value of 1.96. That would be the right tail. Or anything less than the negative of that, negative z-star of our negative 1.96. So z-star equal 1.96 is called the critical value for a 5% significance test. And again, this is when sigma is known. Just like in confidence intervals, if sigma is not known, we'd be looking at a t-star value from the t-distribution, but the interpretation would be the same. We'll see an example shortly. So this gives us yet another way to determine whether to reject the null hypothesis or not. It's called the critical value criterion. We reject the null hypothesis at significance level alpha if and only if the test statistic is either greater than the critical value z-star or less than the negative critical value negative z-star. This is really just another way of saying we reject the null hypothesis if we're if our data is in the rejection region, right? Which is just another way of saying we reject the null hypothesis for this two-sided test if our data is outside the middle 95% in this case for a 5% significance level. Okay, so let's return to this idea of, well, what do we do if sigma's unknown? The answer should be familiar. We're going to be using t procedures and the t distributions in that case. So let's just trace out what happens. Our test statistic, the z-score for x bar, which you see here, is simply replaced by a t-score. And the only difference is we replace the unknown parameter sigma by its estimate, the sample standard deviation S. So when we do that, we get the t-score for our observed x bar. X bar minus mu over the standard error of x bar, which equals x bar minus mu over S, the sample standard deviation, divided by the square root of n. So that's how the test statistic changes when sigma is unknown. The z-score becomes a t-score. What about p-values and critical values? Well, they're calculated conceptually the same way, just instead of using the normal distribution, you use the t-distribution with the appropriate degrees of freedom, which are again n minus 1, where n is your sample size. So let's see a quick example here. Suppose that an experienced realtor believes that the average home price in a certain locality is $100,000. Her younger colleague doesn't agree, but is not sure whether the true mean price is higher or lower. A random sampling of 32 listings yields an average price of $81,588 and a standard deviation of 38,943. What does this evidence say at the alpha equal 5% significance level about the beliefs of the realtor and her colleague? Let's report our results in terms of the test statistic, the critical value for the test, the p-value for the test, and the conclusion of the test in the context of the problem. And by that, I just mean use everyday language like the language in which the problem is stated as to interpret the results of our test to, say, a layperson who doesn't have much familiarity with statistics. So let's start with our hypotheses. As I'm sure you're already guessed, this is a two-sided test. The null hypothesis is the belief that the mean is 100. That's the experienced realtor's belief. Her colleague believes that that's wrong, but isn't sure whether it's overestimate or underestimate. So the alternative hypothesis is that the mean is just not 100. Our sample data is our observed x bar value of 81.588. I should have mentioned that I'm just working in units of thousands of dollars here. So when I say mu equal 100, that means $100,000. When I say x bar equals 81.588, that means x bar is $81,588,000 or $81,588. Just a little more convenient to work in units of 1,000 here. The sample standard deviation was $38,943,000, and our sample size was 32. We're to carry out the test at the 5% significance level. So again, the sort of crucial thing to notice here is that sigma, the true population standard deviation, is unknown. And so since that's the case, we're going to be using t procedures. Let's take a look at the test statistic first. It's going to be a t-score. And there you see it. We're just putting it together. Essentially the z-score, except we're just using s as our estimate for sigma. And that turns out to be negative 2.6745. You interpret the t-score in the same way as you interpret the z-score. In fact, the t-score can be considered an estimate for the z-score, right? So we estimate that our observed data is about 2.67 standard deviations below the mean, assuming the null hypothesis is true. Our critical value, well, here we're doing a 5% significance test, so this would correspond to the critical value for a 95% confidence interval, assuming sigma's unknown. And we know how to do that. So that turns out to be 2.0395, and that comes from the t-distribution with 31 degrees of freedom. What about the p-value? Well, the p-value again is the probability of all t-scores in this case that are more extreme than our t-score. And so our t-score was negative 2.6745. It's a two-tailed test. So the p-value would be the probability of all t-scores that are less than negative 2.6745 or greater than 2.6745. And so you're looking at this time the two-tailed kind of computation of a probability for the t distribution that turns out to be 1.18%. So recall our alpha value was 5%, our p-value is 1%, so we do have that our p-value is less than our alpha value. So by the p-value criterion, we would reject the null hypothesis at the 5% significance level. You can also see from the picture that our observed t-score is in the rejection region of the significance test. It's less than that critical value that we calculated before, if I go back to it, of negative 2.0395, right? It was in that left tail there. So we also could have just observed that since the t-score for x bar was in the rejection region, we're going to reject the null hypothesis, again at the 5% significance level. So our decision then, no matter which way you look at it, is that we reject the null hypothesis that the true mean selling price is $100,000 in favor of the alternative that the mean is different than $100,000. And this is done at the 5% significance level. And the conclusion in the context of the problem is that we have statistically significant evidence at the alpha equal 5% significance level that the average home price is different than $100,000. So that is a quick introduction to the ideas of test statistics, p-values, and critical values. We'll look in our next video at how these ideas play out in one-tailed significance tests. And so stay tuned for that. And in the meantime, take care, and we'll see you real soon.